Hey guys, it's Jesse with another kind of technical video about how turns per second and turn delay works in RTS games that use a lockstep multiplayer networking strategy. Specifically talking about how this impacts Cause Monarchy, which if you haven't heard of it, Cause Monarchy is a excellent RTS built in the StarCraft Brood War engine. Highly recommend checking it out. But really this applies to any RTS, especially the older ones, kind of the 90s, early 2000s Brood War type RTS, where you have a lockstep networking strategy in place. And essentially the way this works is your game has a number of updates that it needs to communicate to other players, and does so on a fixed schedule. I like to think about this a little bit like a bus stop. So you can imagine you've got your game state. Your game state is generating updates, and those updates, that could be like a command, a unit moved, a random thing that happens. Those updates are queuing up at the bus stop, right? And then when the turn schedule comes around, when it becomes time for another turn to be processed, it's kind of like the bus arrives, and all of those updates that you've got queued up, they get in the bus, and off they go to the other users. Now, one of the things that matters, just like in real life when you've got a bus stop, is the schedule of the bus. Right? You can have the bus come frequently. If the bus is coming frequently, you can probably only get a couple of updates, and then the bus comes and the bus takes them all away. Right? You might only have a couple of updates that happen each turn. Or if you have a very slow schedule, you might have a ton of updates that get queued up before the bus arrives, right? Now, this isn't the biggest deal because you can fit a lot of updates on the bus. However, if you do have that kind of scenario where you've got a lot of updates going into the bus at once, what that means is, from the sake of the game's processing, is all of those will be processed all at the same time. It lowers the temporal resolution of the game. Essentially, you could have an order queued up and then another order queued up that undoes that, and they could all be in that same group. So it's good to have the bus come more frequently if you can. However, the problem with that is your networking has to be able to support it. Now, of course, when you're playing a multiplayer game, it's not just about your updates going out, it's also about getting updates from the other players. So if we stretch the analogy a little bit further, it's kind of like when that bus comes in, it's not just picking up your updates, it's also dropping off updates from the other players. And the updates from your game can't actually leave until it's received the updates from all the other players at the same time. And so if that bus comes in late because the other player has a high latency to you, a poor connection to you, then the game will actually have to stop. It will actually freeze until the updates arrive from the other player and are unloaded. And you'll see that as choppy gameplay. If it's consistently arriving just a little bit late, if it's consistently arriving just a little bit late, the game will pause for a split second until all of those updates have arrived, and then it will go ahead and move on to the next turn. Now, one thing we can do about that can help out is adding in a buffer. So the way that works is when the bus comes in, it unloads all of these updates, and they form a little bit of a queue. This is one turn's worth of updates, and the game doesn't process them yet. The game waits until the bus comes back with another set of updates, and then it goes ahead and processes the last turn's worth of updates. This is called turns in transit or user delay, and you can actually have it not just be one turn behind, you can actually have it be multiple turns behind. And this can really help out if there's variable latency, or if there's poor latency, if that connection is coming in slow. Because you're several turns behind, that bus can actually take a long time to get to you, right? And that's actually what the latency settings in Cause Monarchy are. When you go under the game options and you go under network and you change it from low brain cells, high brain cells, extra high brain cells, or low, medium, high latencies in some other games, what you're doing is you're actually adding in that queue, that additional 2, 3, or 4 turns that are pending into the system. What your game is going to do is it knows that it's 3 turns behind on what it's seeing from the peer, and it knows that the peer is also going to be 3 turns behind. And so when you perform an input, like telling a unit to move, for instance, it'll actually wait. It will queue up that update. It will send that update to the peer. Let's say this update here is that move command. The game will know that it's 3 turns behind. So even though it's already sent that to the peer, it's not going to actually perform it locally until it gets to the front of the line, until it gets into the game state on the peer. So it's actually going to intentionally delay processing your user input for however many turns that latency setting is set to. Now let's say you have a really good connection, and maybe you're even playing with someone on a local area network, right? And you want to make the game more responsive, more real-time. You want to really flex those micro skills. Well, you can only do so much by reducing the turn delay, right? You can get rid of these extra steps there, this extra queue, but you always need at least 1 turn delay, because the game can't be working on the previous state and being on the next state at the same time. So if you want to maximize the real-time performance out of that connection, once you've got it down to that low brain cells, the only thing you can do is have the bus come more often so that you're then working on, for instance, maybe only a couple updates, right? And they're coming in more frequently. So once you get to that point, you'll have a higher turn rate. If we're running on 8 turns per second, that means that essentially each turn is 0.125 seconds. Or if we're thinking in milliseconds, just because it's easier to do the math that way, each turn is 125 milliseconds. That means that the game will anticipate receiving the update from the peer every 125 milliseconds. And if you have a turn delay of 2, then that means that the maximum time between the peer sending their turn and you receiving it is going to be 2 times 125 milliseconds, so 250 milliseconds. Right? That's going to be the maximum amount of delay for you to receive that turn. And that includes, by the way, the time that it takes for the game to process it. It's not just the network delay, but all of the other delays intrinsic to the process, right? Now, with a modern network and peers in the same country, that's usually no problem whatsoever. However, if you're playing internationally, you've got somebody in Europe, somebody in Australia, somebody in North America, somebody in South America, what you're going to have is problems where that delay is over 250 milliseconds. And as you have more players, you have to send those updates to each individual player, and you have to receive updates from each individual player. Well, each of these clients will not proceed to the next turn until they've received an update from both of the peers in question. So what that means is the reality of the turn rate is based on the worst connection between all of these players. And as you have more and more players, that can really compound. Let's say you've got somebody in South America, right? Maybe that's a connection that's bad as well. And all of a sudden, you've got to have all of these individual connections, right? And the more and more players that you have, as you go from 4 players, 5 players, 6 players, 7 players, 8 players, etc., the more likely it is that you're going to have one of these connections that's not fast enough to support the turn rate. Okay, so back to the math. If we think about 8 turns a second, each turn is 125 milliseconds. 2 turns in transit. So then that means that you actually have 250 milliseconds to get all of those updates synced up. Now, if we increase that to 3, then you're going to have obviously 375. Or if you increase that to 4, you're going to have 500 milliseconds. So that's what going to, for instance, extra high brain cells does. Now, that being said, this can still be insufficient. So that's where the double brain cells comes in. What we can do is we can reduce this 8 turns per second to 4 turns per second, which means that there's a new bus comes every 250 milliseconds, which means 2 turns in transit is now 500 milliseconds. And if we have 4 turns in transit, now we're up to an entire second of maximum latency. Now, of course, this is getting kind of extreme in terms of the user delay. That means that when you send a command to one of your units, it's going to take a full second before that command gets executed. So this is not going to be a good game experience. However, you're not going to have that situation where you are paused waiting for updates, right? The whole point of that is to not have that choppy gameplay where you're paused waiting to receive updates from the peers. So it's kind of a trade-off. Now that's how you can maximize it for a very poor connection. Let's say you have a really good connection and you want to reduce the input delay as much as possible. If we go back to our 8 turns a second, 125 milliseconds, with this scenario, you're pretty much maxed out at that 250 milliseconds of input delay because you can't actually go down to 1 turn in transit. But what we can do is increase the turns per second of the game. And this can go all the way up to the tick rate of the game, or in StarCraft, I think that's the frames per second, so 24. So this could go as high as 24. So let's see what happens if we change it to 16 turns per second. Well, you can see that we have actually made the turn delay 62.5 milliseconds. And at 2 turns in transit, that means that your max latency is 123 milliseconds. So now it's going to feel very responsive, assuming that you don't have situations where it's not receiving the turn-in time and having to pause the game temporarily. So hopefully that explains it a little bit. Sorry for kind of the rambliness of this video. I'm sick right now, so you probably heard that in my voice as well. But that gives us a little bit of information on what we can manipulate in-game and some of the effects that you get. Thanks for listening, and see you next time.